Here is a list of fun things we're going to examine today. We're going to take a brief review of discrete probability, which is the stuff we talked about last week. We're going to look at assigning probabilities and probability distribution. We're going to look at conditional probability, which is that is our foundation for Bayes' theorem. We're going to look at independent events, and then random variables, and then the Bernoulli trials and the binomial distribution. That's going to be fun when we see that. And then practice as usual. So let's just remind ourselves briefly. I just want to take like 2 or 3 minutes on this. What is the probability formula?
Possible outcomes.
Favorable outcomes divided by possible outcomes, right? And we, in our language, we call that the cardinality of the event set divided by the cardinality of the sample space, right? And again, these are sets. All right, good. And don't forget this is important, that the event set is a subset of the sample space, right? Again, taking a simple example of rolling a die, we roll a die, and we want to know what's the probability we're going to get an odd number. Well, the odd numbers, that's 1, 3, and 5, that is the event set, and the sample set is 1 through 6. So 1, 3, and 5 is a subset of 1 through 6, right? So here's a question for you, and this will be our only example to remind us about how this stuff works from the other day. What is the probability that I will draw a heart from a deck of cards? Not the final number, but just the calculation. What's that look like?
13 divided by 52.
13 over 52, right? So what's our sample space? The sample space is ace of hearts, clubs, diamonds, spades, 2 of all those, ... all the way up to the kings, right? That's 52 playing cards. We're going to assume there's no jokers in the deck. And then that is a total of 52. That's the cardinality of that is 52. And then what is our event set? And what is its cardinality? Well, we already said all these numbers. The event set is ace through king of hearts, and the cardinality of that is 13, right? So I just want to make sure we understand the terms. This is just a review from the other day. And if we do that math, so we look at our purple formula up there, we swap out the numbers there, we get 13 over 52, which is 25%, right? Which makes sense. A fourth of the deck is hearts, a fourth of them is clubs, diamonds, and spades. Okay. Questions about the basic review there, the premise of it? Now, what have we been assuming in all of these scenarios? We made a couple of assumptions for all these problems. There are 52 cards in the deck, that's true. Let me rephrase the question. What have we been assuming in all of our probability scenarios, like from last week, with dice, coins, cards, everything? That they're all fair, right? There's no weighted scenarios, right? That all, and the other thing is that, in other words, they're all equally likely, right? The getting a head is equally likely as getting a tail. Drawing a heart is equally likely as drawing not a heart, okay? Well, not quite, but any given card from the deck is equally likely to come out, right? So here's some questions that we're going to look at today. They're interesting questions. I'm glad that you guys are close to the speaker because I like having your laughter on the computer. Oh, all right. It makes this classroom seem fuller too. All right. What about non-fair items? What about weighted coins, loaded dice, right? Decks of cards that are stacked against you because the magician can influence which card you're going to pick, right? These are all things that are in my repertoire, all right? So if a fair flipped coin lands tails, this is an interesting question. It's a new question. If we flip a coin, it lands tails, it's a fair coin. What's the probability that the next 3 flips will be heads? Okay, and I'm not going to answer that right now. We're going to talk about these kind of questions. If a coin is flipped 100 times, what's the probability that exactly 40 of them will land heads? Another thing that we're going to learn about how to do that kind of stuff today. This idea here, when we're dealing with non-fair items, we call this weighted probability. The next idea here, when we're dealing with if the first event does this, what's the probability that the next event will be this? That's conditional probability, and we'll be talking about independence as well when we get to that subject. This last idea here, that if we flip a coin 100 times, what's the probability that exactly 40 of them will be heads? Deals with random variables, which ironically, I think ironically is the right word here, random variables are neither random nor are they variables. I'm not kidding. That's actually, that term comes from a lost in translation moment from the original Italian phrase. I don't remember what the Italian phrase was, but when it got translated to English, it became random variables. What it is actually just a function, okay? We'll see about that a little bit later, but we'll be talking about that. So let's take an example here, a scenario, dealing with the assigning probability. Let's let S be the sample space of all possible outcomes. And so an example, again, would be our deck of cards. Also note that, and these kind of things always hurt my brain when I try to read them, when you have the things surrounding the less than or greater than symbols, right? But all we're saying is that this little s here is an element of big S, right? So in other words, ace of hearts is a potential S, little s, right? And ace of clubs is the potential little s, and the nine of diamonds is the potential little s, right? For every single little s, every single element of the big set, the probability of that being the chosen thing, the event, is going to be between 0 and 1, right? We already kind of know this. We've talked about this. Because remember, any given event will be a subset of the original set S, right? So just getting an ace of spades or hearts or diamonds, that is a subset, right? That's one possible outcome, right, in our event. Does that make sense? Right? So we're looking at this, we're basically saying that any S, any element of this sample set could be an outcome we're looking for. Maybe it's not, but remember, we're talking about what are our favorable outcomes. Well, maybe any one of those 52 could be one that we someday might want it to be one of our favorable outcomes, right? That's basically all we're saying. And the probability of any given one of those is between 0 and 1. Any given thing in there, the probability of any one of those would be 1 over 52, right? The probability of getting an ace of hearts is 1 over 52, ace of clubs 1 over 52, and so forth, right? So it would always be between 0 and 1. Now, if we have a single element, one element in our sample space, and we want that to also be our event, then yeah, the probability of getting it is 100%. But we're going to be dealing with a large set, something that's finite, but not just one thing. So in that being the case, the idea that we're building to here is what is the probability of each individual thing in that sample set? And this is what we end up with, okay? Now look closely at this. What we're saying is that if you sum up the probability of every single element in the set, it will equal 1. Does that make sense? Right? And I think the next slide shows that in a little bit more detail here. Right, and this still fits our original idea here, right? Doesn't this still hold true? Because what we're simply saying here is, rather than having this outcome of, hey, this is what we're looking for, an odd number or a heart or a club or whatever, we're just saying we want this one card or that one card or this one card. We're just looking at every single element in the sample set as a potential event, right? And so we're looking at what's the probability of event 1 out of 52 and event 2 out of all 52. And each of those events individually is every single playing card in that set. Does that make sense? So this still fits the mold here. And here's another way to look at it. And this is basically saying the same thing as that third bullet point above. That if we have think about this like a for loop in our programming world. For I equals 1 through n, 1, 2, 3, 4, 5, 6, all the way up to n. If you were to take the probability of x1, xi, which is one element in the set, or 2, the second element, or the third, or the fourth, or the fifth, or the nth, and you were to add all of those up, each one of those individually will be between 0 and 1. This is just another way of saying the same thing we've already said. This sum here, if we were to add each one of those things up, the probability of every single individual element in the set, if you were to add up the probability of any given one of those happening, all of them happening, one at a time, each of their own probabilities, it would add up to 1. Do you understand that? Okay? So the example here, to show you, we're back to our sample set here of 1 through 52. Well, the probability of getting an ace, plus the probability of getting ace of hearts, plus the clubs, plus the diamonds, all the way up to the probability of getting the king of spades. If you add all those together, it's 1. 100% of the time you will get one of those 52 cards, is all that's saying. And this is another way to think of it, right? The probability of getting the ace of hearts is 1 out of 52. The ace of clubs is 1 out of 52. Ace of diamonds, 1 out of 52, all the way up. The probability of getting any one of those at any given time, the total of all of them is 1. All right, this idea, we call this probability distribution, right? What is the probability of any one of those events in the sample set? Again, assuming this is a fair, or sorry, not fair, but each event is equally likely. But even if they're not equally likely, the probability of any given event plus the probability of the next event plus the probability of the next one, each element, I should say, will always add up to 1. If I have a biased coin that lands heads 90% of the time, right? Well, the probability that I'll get a head is 0.9. Probability that I'll get a tail is 0.1. Add those two together, that's the probability of everything in the sample set, head or tail, that adds up to 1, right? The probability of any given thing in the sample set, all of them added together, will be 1, 100%. 100% of the time, you will get something from that sample set, right? Some event, right? So let's look at this idea of uniform distribution now. Where n is the number of elements in the sample space S, starting there, we assign the probability of 1 over n to each element in the sample space. Using our deck of cards there, right? What's n? N is 52. So every single element is 1 over 52, assuming that they all have the equal same likelihood of happening. So any questions about this idea? This is going to lead us down some paths here in a minute, but I want to make sure that basic foundation makes some sense. We feeling okay about the idea there? I know it's pretty simple, but it starts to get a little bit more, I don't know if convoluted is the best word to say, but it gets a little bit trickier as we go, okay? All right, so now using this concept, what probability do we assign to the probability of getting heads and the probability of getting tails for a fair coin? And then what about a biased coin where heads is twice as likely? So let's look at how this would play out. What do we assign the probability for getting heads and for getting tails with a fair coin? Yeah, 0.5 for each of those, right? Pretty straightforward. If it's a fair coin and it has an equal, and again, we're leaving out the possibility of landing on its edge. There actually is a coin, I think it's in the UK, that if you flip it the way it's designed, there's probably like a 10% chance that it'll land on its edge. Maybe it's a little less than that. There's a video that I can't remember his name, Matt something. He's one of the dudes that you'll see on Number File sometimes. He did a video about probability, and he was talking about that. And he actually tested out how many times it would take to get it to land on its edge. During his seminar, he did it, and it landed on the edge, but then it rolled off the table, and it kept rolling and staying on the edge, and it was about to stop, and then it actually tips over. But it almost got it on the first shot. Anyway, but our coins in America, most of them aren't going to do that. They have the little notched edges, you know. The only thing that doesn't really is the nickel, and it's pretty thin. The odds of it landing on its edge are pretty slim. So we're going to rule that out. Just heads and tails. So the first one, yeah, probability of heads is 1/2, probability of tails is 1/2. Easy enough. But what about the next one? How do we do that? Now, keeping in mind what we know now about distributing a probability, and we know that the sum of every single probability of every single event in the sample set will eventually equal 1. So what can we do? So you could add another head to the sample set, right? Let's see how that plays out mathematically. Do we agree with this statement? Whatever the probability of tails is, we don't know yet. I mean, we kind of can see it because it's pretty simple, small numbers here. But let's just say it's a bigger thing we don't know for sure, right? We do know this is true. The probability of heads is the same as the probability of tails times 2. We all agree with that? Okay. Next up, we also know that the probability of heads plus the probability of tails is 1. That's our uniform distribution rule, right? So with that, we can do this. We can replace probability of heads with 2 times the probability of tails. That word's starting to get old, saying probability a lot. I'm not enunciating it very well. So 2 times the probability of tails plus the probability of tails is equal to 3 times the probability of tails. Would you agree with that? Which should equal 1. Agree so far? Therefore, mathematically, if we rearrange all this, 3 times the probability of tails equals 1. In other words, the probability of tails equals 1/3. That's just algebra, right? Now, if that is 1/3, then of course, we know that the probability of heads plus tails is 1, which means that the probability of heads is 2/3. All right, so questions about that basic idea there? Doing okay? So this is how we can figure out when we have weighted objects, what is the probability of any one of those that are weighted? And we'll see some more samples of this in a little bit. So let's take a look at the definition of the probability of an event here. And we already kind of know this, right? The sum of the probabilities of the outcomes in the event set E, using this formula here. This is the same idea that we talked about a minute ago, but now we're looking at the event set, not the sample set, right? Before, I was using this exact same sigma notation, summation here, to show us the probability of every single individual element in the sample set. Now I'm doing the same thing to look at every single element in the event. And what is the event? The event is all of the outcomes, the favorable outcomes, right? We call the set of favorable outcomes, we call that the event. So the probability of the event is the sum of every element in the event probability. Make sense? So I think I got some more pictures to explain that a little bit better. And this is the same formula again that we looked at a minute ago, where we just do a loop from I to N, or from 1 to N. And that should be a little subscript I right there. I'm gonna not edit it, but that should be a subscripted I, right? And so it's if we loop through, the probability of each element in the event, the probability of the event is the probability of each of those events, the sum of them. Now, notice that does not add up to 1. Our other formula with the sample set added up to 1. Why does this not add up to 1? Well, the total of the probabilities, though, why does it not add up to 1? In the sample set, the total of each probability of the sample set, each element added up to 1. Why does it not do that in the event set? Because the event set is not necessarily the entire sample set, right? Again, rolling the die, getting an odd number, 1, 3, and 5, is only 3 out of the 6 possible things, 1 through 6, right, on rolling a die. And so the probability of the event, which we already know, it's the probability of getting a 1 plus the probability of getting a 3 plus the probability of getting a 5, right, the odd numbers. That does not add up to 1. But what that will add up to is whatever the probability of cardinality of E over cardinality of S, right? So this is the same thing we learned the other day. This is just a little bit more details that can help us moving forward, and it's a little bit more formalized, if you will, okay? Also, don't forget this. This is important to remember, right? The probability of the event occurring and the probability of the event not occurring is equal to 1, which is why that first thing does not add up to 1. If you add up what we left out of the event, the 2, 4, and the 6, plus the probability of the 1, 3, and 5, that will add up to 1. So we're going to use an event of ace through king of hearts out of a deck of 52, right? But our sample set is ace through king, all the cards, all 52. But our event is just ace through king. So the probability of ace of hearts is 1 out of 52, 2 of hearts, 1 out of 52. You add all those up, and you end up with 13 over 52. Agreed? Well, that's going to be a total of 25%. That does not add up to 1. But if I add up the probability of ace of spades, 2 of spades, 3 of spades, ace of clubs, and so forth, all the way up the whole deck, plus this, then that would add up to a total of 1. So it's the favorable outcomes is getting a heart, the probability of that entire event, plus the probability of not getting a heart, which is spades, clubs, and diamonds, which is 75% of the time, right? You add that together and you get 100%. We feel okay about that? And all I've done really, most of everything we've covered so far is restate what we already know in a little bit more detailed terms. So hopefully this makes some sense, and then moving forward, we're gonna see how to apply all this stuff, right? So let's take another example of assigning probability here. Assume we have a loaded die, and the die, a 3 will appear twice as often as each of the other numbers. I actually have a dice like this. I have dice that I can make any number never appear. I have dice that I can make only one number appear every time. I've got a set of dice that if you roll them, you'll always get a 7 or 11. I've got a set that some dice numbers are more likely to appear than others. And if we weren't recording this on the PowerPoint, I'd show them all to you. So you guys are gonna have to come back in the fall for just today's lecture. All right. So the other 5 numbers are equally likely, right? The 1, 2, 3, or 1, 2, 4, 5, and 6. The probability of any of those is the same as each other, but the probability of 3 will appear twice as often as the other ones. So what's the probability that we'll roll an odd number? That's the question. It's a regular die as far as it has 6 sides, but that 3 is going to come up twice as often as a 1 or a 2 or a 4 or a 5 or a 6. What's the probability that we'll roll an odd number? That's the question. So let's first look at what is our event set. What are all of our outcomes? 1, 3, and 5. All right, very good. Yep, 1, 3, and 5. Okay. Next up, what's the probability of 1 or 2 or 3 or 4, or it's not 3, but 4, 5, and 6, right? Not everything but 3. What's the probability of each of those? We don't know that yet. We're going to get there mathematically, yeah. Okay, but yeah, you're right. So we don't necessarily, again, imagine bigger sets and things. These are small ones so we can see them. But what we do know is this, that they're equal to each other. That's just given to us in the problem, right? Probability of 1 is equal to probability of 2, and down the line, we just don't know what that number is exactly, but they are equal to each other. So what is that number? That's what we're trying to figure out. We say it's 1/7. Why? This is what Craig said a minute ago. Why is it 1/7? You said 1/7. What made you say that? Yeah, so it's like you were saying earlier, adding a second head to the set of the sample set, tails, heads, right? Same idea here. We're going to add our sample sets basically 1, 2, 3, 4, 5, 6. So there's 7 things. So we know this to be the case now. Now, using all of our little additions and things we've learned about today, What's the probability of getting a 3? 2 out of 7, right? Why? Yeah, because there's 2 3s in that event set, right? And in this scenario, we are treating those like different elements, right? Because when we start talking about cardinality and we're like, well, wait a minute, there's 2 3s, why would the cardinality be 7, right? We're treating it like a different 3. It's just a little trick of the mind to make the calculation come out properly, right? Does that make sense? So it's 2 out of 7, correct. Now we want to figure, we still haven't answered our question though. What's the probability of getting an odd number? Well, what do we know about the probability of our event space? Our event. What do we know about that? We did our little funky formula on the page before with the sigma notation. Yeah, it's the probability of getting a 1 plus the probability of getting a 3 plus the probability of getting a 5. That's a hard word to say 5 times in a row, right? So we have this given here now. And so the probability of our event is exactly what I just said. It's 1/7 plus 2/7 plus 1/7 again. Dig it? So a total of 4/7. So the probability of getting an odd number is a little better than it would be if we did not have a loaded die, which that passes the sniff test too, right? Okay? So here's the idea of conditional probability, right? Conceptually, it's this. Given that event F has occurred, what is the probability that event E will occur? This is the idea here. We're trying to figure out if we know this one event already occurred, what's the probability that this other event will occur? So in other words, what is the probability of E given F? And this is the crux of what we're trying to learn today. This is the big foundational idea that gets us into Bayes' theorem. What is the probability of E given F? This is what we're going to learn about, how to figure these out, how to calculate these. So here's an example. A fair coin is flipped 3 times. All 8 outcomes, that should be plural outcomes, and I'm not editing it. All 8 outcomes of a batch of 3 flips are possible. You guys understand what I mean by that? Tails, heads, heads, tails, 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 heads, heads. Every possible version of 3 coin flips is an available option, okay? Given that the first flip was a tail, what is the probability that an odd number of tails appear? Okay, this is the question. Given that the first flip was a tail, what is the probability that the number of tails that appears will be odd? This is what's the probability of E given F. This is the idea, okay? So how do we solve these kind of problems, all right? Here's how it works. First of all, let's look at the possible outcomes. Just start there, our sample set. That's our sample set, right? There's no other way to flip 3 coins. You agree with that? Okay. How do we know that? 2 to the 8th, right? 2 to the 3rd, sorry. 2 to the 8th. That's a lot bigger number. 2 to the 3rd, right? Because it's 2 possibilities, heads or tails, and we're doing 3 flips, right? Okay. But the idea was given we flipped a tail first. Well, that's only these purple ones, right? Okay, so given that we flipped a tail first, what's the probability that we're going to have an odd number of tails? That's a different question than just what's the probability we'll have an odd number of tails, right? So what is the probability we'll just have an odd number of tails? Forget what's given. If I just said, I'm going to flip 3 coins, what's the probability that I'm going to have an odd number of tails? What's the answer? Yeah, 4 out of 8, right? Which is half, 50% of the time. Now, coincidentally, flipping the first one being a tail, the probability of having an odd number of tails is still 1 out of 2, 2 out of 4 in this case, right? Which is still a half. Do you see that? Those are the only 2 that are odd, okay? But what changes here is we know the first flip. It's a given that the first flip was a tail. So what's the probability out of that new sample set, right? That becomes sort of the new sample set. What's the probability that the event odd number of tails will happen? It's 2 out of 4. That make sense? We've already talked about that. I really should have my slides more. Okay, so here is this looking at this idea generalized, all right? Finding E given F, we use F as the sample space, right? That's the thing that happened. In this case, the tails was the first flip. That's the new sample space. We're not looking at it over all of the flips. We're only looking at it over those 4 flips where tail was first. So formally, it looks like this. Now, this is tricky to see at first. That first thing on the left there is pronounced the probability of E given F. That's what that little such that marker means there. The probability of E given F. Well, what is that? It is, now look at our sample set on the bottom. Remember, what is the probability of anything? It's the cardinality of the event over the cardinality of the sample space, right? Well, in this case, what will the cardinality of our sample space be? It will be the probability of F occurring, right? And the probability of our new E is whatever the probability of the intersection of E and F occurring, that both events happened, right? That a tail was flipped first and an odd number of tails occurred. Do you understand why that's the intersection there? Okay? So let's take a look at a picture of this. So this is every scenario here, right? This is a Venn diagram here showing that our universe over here, as we can see, our universe is all of the possible outcomes. Would you agree that all 8 of them are there? Right? And then E, we're calling this set E here, is all of the times that we had an odd number of tails, which is those 4 cases right there. Agreed? F right here is the scenario where the first flip is a T, which is all those cases there. So that being the case, my little blue squares also sort of made their own Venn diagram. Do you see that? With that intersection between in right here. That is the case of it. The first one was a tail, and there's an odd number of tails. That's the intersection of E and F occurring, right? So that is this divided by our sample space, which now is just the event that a T was first right here. Make sense? So that's the formula for that, okay? How do we feel about that idea? When you see it and we explain it, it's easy enough to go, yeah, that makes sense. But then remembering it and applying it, right, it gets a little trickier for sure. Okay, so I'm going to leave that on there for another second here, just make sure we're good. We have no other questions about it.